Chapter 26, Part 1, we are going to talk about chi-squared goodness of fit. Now, in this next section, what we're going to do is look at hypothesis testing and confidence intervals for categorical data. Okay, so we're not going to be given number values or quantitative data. Instead, we're going to switch gears and look at categorical. So to get us thinking in kind of the right direction, we're going to start with this little opener activity looking at a bag of M&Ms. So Mars, the company that makes M&Ms, claims the following distribution. 13% are brown, 14% yellow, 20% orange, 16% green, 24% blue, and 13% red. However, the mix of colors has been known to change every few years. Our task today is to determine whether or not the current mix of colors matches that of 1995. So that 1995 data is the one that we were given up here. We want to see if there's sufficient evidence to reject the company's 1995 claim. So we're trying to prove whether or not this claim that they made back in 1995 is still accurate. So to do this, we're going to have to look at a new type of test, which is called a chi-squared goodness of fit test. So what a goodness of fit test does is it tests how well does our data fit this information that's given to us. Okay, so here's our quote bag of M&Ms. I apologize, I didn't think to print this in color. If you look at Canvas, you can see a screenshot of this bag of M&Ms to look at your colors more clearly. I did go through and label them, so we're going to go through right now and just count how many of each color are in the sample. This is called our observed values. It's what we are observing to happen in our sample. So brown M&Ms, we should get 5 of them. Yellow, I'm getting 4. Orange, only 2. Green, 1, 2, 3 green. Only 1 blue. And let's see, red, 1, 2, 3, 4, 5. Okay, there should be 20 M&Ms in total, so let's quickly check, make sure that I counted those correctly. So I'm just going to do 5 plus 4. That does give me 20. Okay, now I know that we're trying to prove whether or not their claim in 1995 was accurate. We're trying to see if this current mix of colors matches. So what we're going to do is quickly create some hypotheses here. I'm still going to have 2 hypotheses, my null hypothesis and my alternative. And a good assumption, or something that we always want to start off with thinking, is that their claim is correct. So what I'm going to say is that the current mix of colors that we have right now matches 1995. That's what I'm going to assume to be true. So I'm going to say our sample will match the 1995 claim. We're trying to see if that 1999 claim is true. I don't really care if there's more brown than they claimed, or if this percentage of orange is actually higher or actually lower. All I'm trying to do is figure out whether that claim is true or false. So my alternative hypothesis will be that it does not match that 1995 claim. Okay, that not matching could mean a wide variety of things. It could mean that there's more yellow. It could mean that there's less blue. It could mean anything. I'm just trying to prove whether or not that claim is true or false. Now, in our first hypothesis, we said that our sample will match the 1995 claim. So what we're going to do is start with supposing that that M&M's claim distribution is true. If they are correct, I want to find how many of each color we would expect to get in our sample. So this is our expected values, not what actually happened in our sample, but what we would have expected to happen. So if I opened up this bag of 20 M&Ms, we would expect, go back here, 13% of them to be brown. So what I'm going to do is take my calculator, I'm going to find 13% of 20. Okay, now 2.6 doesn't fully make sense. I can't have 2.6 M&Ms, so I'm going to round that to 3. And I'm going to keep doing this, just taking the percent that they gave me and comparing it to my sample. So 0.14 times 20, 2.8, so I'm going to assume 3 here again. Actually, guys, I take that back. We're not going to round here for expected. I know it doesn't really make sense to have those decimals, but for our expected values, we are going to leave them as decimals. Okay, I'm going to keep going here, taking my orange, so 20% of 20 is 4. Green was 16% of 20, 3.2. 24% blue, 4.8. Red, 0.13 times 20, 2.6. And when I add these up here, I should still get 20 total M&Ms. So let's just double check. Good, I do. Okay, so our observed values should always be whole numbers, but oftentimes those expected values will be decimals, and that is okay. Okay, now since we're using a new distribution, since this is a chi-squared, we need a new test statistic. I can no longer use a z-score or a t-score because I have categorical data here. So instead what we're going to use is called chi-squared. Chi-squared looks like kind of a fancy looking X. I usually draw it like this. One side squiggled, the other side straight, and then it is squared. Okay, our formula to calculate chi-squared says to take the sum of our observed values minus our expected. Now, some of those could be positive, some could be negative, right? I could have more expected than I observed. So in order to get rid of those positives and negatives, we square it, and we divide by what we expected. So we're going to go through here and use this table to calculate our chi-squared. I'll do maybe 2 of them with you, and then pause the video and have you guys try the next ones. So I'm going to start with listing how many brown M&Ms we observed. We observed 5 of them. We expected 2.6. I'm going to find that difference. So 5 minus 2.6 gives me 2.4. So I just did the observed minus expected. I want to find the squared of that. So I'm going to take 2.4 and square it. That gave me 5.76. And I now want to take that value and divide by what I expected to happen. So I'm going to take that 5.76, divide by 2.6, which gives me this first one. I'm going to round a little bit to 2.22. Okay, that's just for my brown. So we're going to go back and we're going to do the same thing now with yellow. So yellow, we observed 4 of them. There were 4 yellow M&Ms in my sample. Based on the data that was provided to us by Mars, we expected to get 2.8. A little subtraction there gives me 1.2. Squaring the 1.2 gives me 1.44. And again, I'm taking that 1.44 and dividing by the expected. So 0.51. Okay, go ahead and pause your video. I want you to finish this for orange, green, blue, and red. So here is my table filled in. Again, I just went through that observed minus expected, squaring it, and then dividing by the expected value. Okay, once we have all of these numbers right here, we want to find the sum of them. So in our calculator, let's just go ahead and add all of these together. So I'm doing 2.22 plus the 0.51 plus 1 plus 0.01 plus 3.01 plus 2.22. That gives me my final answer of chi-squared is equal to 8.97. So essentially what we just found is if we were to draw a picture here, which since we're now looking at chi-squared, our picture changes a little bit here. Chi-squared distributions are skewed to the right. So I'm going to draw something that has a bit of a skew to that right-hand side. We just found that our chi-squared is at 8.97. That's kind of our drop down, just like we would do for like a t-score or a z-score. Now on the AP exam, you don't really need to know about the shape of that chi-squared. What we really care about is finding this chi-squared value. Now I'm here to give you good news. Go ahead and turn your page. Although that wasn't too tricky, it did involve a decent amount of work filling out that entire table. Luckily for us, the AP exam does not require that we show our work when calculating the chi-squared. Instead, we can just use our calculator. So to use that calculator, what we're going to do is go to Stat, Edit, and we're going to type in your observed data into OneList. I usually put my observed data in L1. So I'm going to do that M&M example. We had 5 brown, 4, 2, 3, 1, and 5. In the L2, we would put what we expected to happen. Right, I usually just recalculate these. So I would do 20 times what they told me for brown, so that was the 0.13. We're not going to have to write down our expected values sometimes, so it's nice just to put them in there. Since we already calculated, we could just type them all in. We're then going to go to Stat, Tests. We're going to look for chi-squared goodness of fit. It's going to be called GOF. It's close to the bottom here. Your chi-squared just looks like an X to me, really. But we're looking for that goodness of fit because we're testing how well or how good our data fits the distribution that was given to us. Our observed should be in our L1. Our expected is in L2. Degrees of freedom you always find by taking one less than the number of categories. So there were 6 colors here, so our degrees of freedom will be 5. We can go ahead and hit calculate. It's going to give us our chi-squared, which they had 8.965, which we got 8.97, which means we did everything correct. I do want to go back real quick to that same test, but I'm going to go to draw so you can see that skew in your chi-squared. So if when you were taking this test or the AP exam, you're like, shoot, I remember that chi-squared looks a little bit different, but I can't remember where or why it looks different, you can just graph it on that calculator, and it gives you the picture. Hey, let's do another quick example, just getting used to finding that chi-squared on our calculator. So example 1 says, Carrie made a 6-sided die in her ceramics class, rolled it 80 times to see if each side was equally likely to show up. And she wants to see if this is a fair die. So the table below summarizes the outcomes of her 80 rolls. So the outcome of the rolls would mean that the die landed on 1, that happened 10 times. 2 happened 26 times, giving her a total of 80. We want to state the hypotheses that Carrie should use. So we are trying to test if the die is fair. I don't even want to think about her data because looking at her data right away, I'm like, oh, they're like all over the place. I don't think that it's a fair, die. I don't think each side is equally likely to happen. But that is what I want to assume. Just like I assumed in the beginning that our M&Ms would match whatever the company told me, I am going to assume that each of these rolls is equally likely to show up. So I'm going to say each side is equally likely. Okay, alternatively, I'm trying to show that each side is not equally likely. I don't care which side shows up more than the other. All I care is that it's not equal. So each side is not equally likely. Okay, we'll complete this chart real quick, and as I complete the chart, I'm going to type it into my calculator at the same time. So our observed values is what we observed in the sample. This is what actually happened. So that was right up here. An outcome of 1 happened 10 times. 2 was 26, 11, 11, 9, and 13. Okay, let's go ahead and type those observed values into our L1. Okay, in L2, I'm going to find what I expect to happen. This expected value always goes back to that null hypothesis. So in our null hypothesis, we said that each side was equally likely to occur. So I have 6 possibilities here. If they're equally likely, that means that there's going to be a 1 out of 6 chance that each of them occurs. Okay, I'm going to type these into L2. What I want to do is just take the total number of rolls that we had, so 80, and multiply it by the 1/6. That's the chance that I'm going to land on a 1. It gives me 13.33. Each of them should be equally likely, so I'm assuming here that all of these will be 13.3. So this one's a little bit different than that M&M example because we were just having each side be equally likely. It's strange that our expected values are all the same versus the M&M one, we had like different values for each category, and that's totally fine. Okay, calculating the value of our chi-squared, we're going to our stat tests. I'm looking for chi-squared goodness of fit. Observed, is L1. Expected was in L2. Again, degrees of freedom is 1 less than the number of categories. I had 6 here again for the 6 sides of the die. So 1 less than that is 5. And we're going to calculate. Okay, our chi-squared is 15.1. Okay, I know it doesn't say it on there, but I do want to draw that picture again. I'm a little lazy, so I'm just going to use my calculator. I'm going to go back to that goodness of fit test and go to draw instead. Okay, this is so far away that we can barely even see it here, but my chi-squared is here at 15.1.